Good morning and welcome to the next chapter. You've all done really well on vectors. I was very, very happy with the work I was seeing produced. Do carry on plodding away through that, and also if you do need any help, just do let me know. Communication is key. Now, the next chapter is hopefully there's going to be a lot of revision for it. So we just need to just go over some basic stuff. I'm going predominantly from the book here, but it's very important uh, to make sure that we're very, very certain on some things. Okay, so we're talking about probability. Probability. Okay, that's what this entire chapter is about. It doesn't get any harder than the probability stuff. Doesn't get any harder than this. Now, let's just do a recap. P of H equals 0.5. What's H? It's a coin flipping on heads. And P of T also equals 0.5. Now, important, probabilities can be decimals or they can be fractions as well. Both are acceptable. Sometimes it would say in an exam situation to use either the decimals or a fraction. You guys need to be able to use both. Personally, I recommend using fractions where you can. It makes some of the things later on a little bit easier. So let's just do another quick example. P of 1 equals 1 over 6. What's 1? Probability of rolling a die, of rolling a 1 on a die. Of course it is. Now, the probability of a even number on rolling a die, well, what's that going to be? Well, we all know that a die you can have 1, 2, 3, 4, 5, and 6. Those are our outcomes. So probability of an even number is going to be, well, which are even? That one, and that one. And so this tells us the fraction. This tells us our probability. In case you've forgotten, 3 out of 6, where 3 is the total number of ways to get what you want. In the book, it says number of successful outcomes. Again, I don't really like the way it does that. And 6 is the total number of possible outcomes. Okay, so the probability of oh, sorry, that will equal. Now, this is where it gets a little bit not hard, but just as a reminder that 3 over 6, that is like our raw probability. We can cancel that down to a half, that's fine. But it's all important to know that if you've got that half there, it's a different fraction from 3 over 6 because that one now no longer, it doesn't represent the number of ways you can get what you want. And there are not only two things. So let's delete that. So when we're talking about probability, another important thing is the probability. Well, let's do the probability of 1 dash. Okay, that means the probability of not a 1. Okay, so the probability of something which is not the thing that you're trying to get. There are ways of doing this, and you've got to know both of them, because if you want the probability of not a 1, then it's going to be the probability of a 2, or, remember it's plus for or, probability of a 3, or probability of a 4, or probability of a 5, or probability of a 6. Oh, my hand's tired already. These are all the same probabilities. They're all 1/6. Okay, add them together, we get 5 out of 6. Now, that makes sense because the probability that you roll any number must be 100%. So the probability of getting a 1 plus the probability of not getting a 1 must be 100%. It must equal 1 because you can't roll anything else. You can either roll a 1 or not a 1. So one of the really nice ways of doing these calculations quickly as well is not just by working it out the long way that way. That's boring. That's no, we don't like that. We like to use this one instead because this here is just an equation, right? We've got. Let me just delete that 100%. We don't use percentages anymore. That equals 1. So the probability, if I want to work out the probability of not a 1, well, I can take away probability of 1 from both sides, and I get probability of not a 1 equals 1 minus the probability of getting a 1, which is 1 minus 1 over 6, which is 5 over 6. Yes. Happy this one. Not so happy that one. The reason I say it's not happy because you can see it just takes a long time to get. It takes a long time to do it. That's all. Okay. So these are the bare bones of probability, and I'm going to go through just a couple of examples for you guys to make sure that we're doing it correctly. Generally speaking, tree diagrams are your friend. Now, don't worry. I'm going to go over each one, tree diagrams one by one. And this one here was none of it because that was just a little introduction, right? Now there is also, there's one more thing that I just want to, I've chosen a couple of examples from the book. This one is on page, what page is it on? It's a 1-star page on page 252. Okay, so page 252, first one. Now it says copy and complete the tree diagram. I'm not going to do that, but one thing I can do is I can just fill out the diagram on here, and it uses the information that I just talked about a minute ago. Because if you're playing a game, right? It says a hook a duck game. So you've got a fishing rod and you're trying to pick up the duck. You win a prize if the duck's got an X underneath it, and he picks one at random and then picks another one. The actual diagram there doesn't mean anything. But what I think you can say is that you can either win or lose. You can't tie at this kind of game. So you must have to be able to win or lose. So if I know that the probability of winning is a fifth, then I know the probability of losing must be 1 minus a fifth. Okay, so that must equal 4/5. Now, one thing that you can always check is that if you have a branch, 2 branches coming out of as options, then they will always add together to give 1. Then the second game is also going to be win is 1/5, lose is 4/5, and win is going to be 1/5, and lose is going to be 4/5. Okay. Now, this is because one of the reasons that I'll talk about in a minute is because each time you play the game, the duck gets put back and you pick another one. So each game has 0 effect on the next game. We will discuss that in the next example, do not worry. So we've done that bit there, that's easy. Now, what's the probability of winning 2 prizes? Okay, so now we start to look at the different possible outcomes. So I can see that if you want to win 2 prizes, there's only one way of doing it. You go win, followed by a win, right? So that means you need a win and a win. Now, do you remember? Of course you do. A win and a win, you don't add them, you times them. If it's or, plus, and times, okay? I think the or is quite straightforward to understand why you add them. because you either win or lose, and 1/5 plus 4/5 must equal 100%. So it must you have to add them. Why you times them is a bit more complicated. We're not going to get into that right now. So win and win. Well, I know that that's going to be, therefore, it's going to be a 1/5 times 1/5. And times in fractions is easy. It's just 1/25. In fact, let's do that for all of those different, for all of the different possible outcomes, right? So I've got win is 1/25. I just worked that out. What about win lose? Well, that's going to be 1/5 times 4/5. It's got to be win and lose. So that's going to be 4/25. What about the next one where I've got lose and win? Well, that's going to be 4/5 times 1/5, which is the same probability, because it doesn't matter which way, because essentially it doesn't matter which way round it is. You either win first or second. It doesn't affect the probability. Now, what about the last one? Well, I'm not going to work it out. I'm going to work it out the smart way, because I know that this is the only, lose is the only other possible way. So I know that 1/25 plus 4/25 plus 4/25 plus the probability of lose equals 1, right? So those together give 9/25 plus something equals 1. Well, what have we got left? 1 minus 9, 25 minus 1 is 16. Yeah, that's right. So 9/25 plus 16/25 equals 1, because there's no other possible outcomes. So without doing any multiplication of different possibilities, I can work it out to be 16/25. Now, does that also make sense? 4/5 times 4/5? Yes. 4/5 times 4/5 also equals 16/25. So there's these two things, there's the two approaches that you have to be able to recognize and just understand and be able to use as and when you want. So let's go back to answering the questions in the question. Winning 2 prizes. So one, well, we've got that. Winning 2 prizes is going to be 1/5 times 1/5 equals 1/25. Always show your working, people. Question 2, winning nothing. So that's going to be lose. So that's 4/5 times 4/5 is 16/25. Winning 1 prize. Now, this is something that you've got to be just a little bit careful of, because let's have a look. How many different ways can you just win 1 prize? Well, you've got probability of win, lose, or probability of lose, win, because that would have the outcome that you win once, which is what we want. Great. Well, have we got that? Win, lose? Yeah, we know that is. That's 4/25 plus 4/25. Well, that must equal, therefore, 8/25. So that's the probability of winning just 1 prize, exactly 1 prize. For the fourth part, winning at least 1 prize. So we're going to have WL plus or LW, or probability of win-win, because 2 prizes is still okay for that, still satisfies us. So we've got 4/25 plus 4/25 plus win-win, which is 1/25, which equals 9/25. So having a good diagram, a good tree diagram, is absolutely essential. Okay. Now I'm only going to do one example from each one, because I think you should be okay. You should be okay. Let's go to the next one. This one was independent. Yeah, because each time it's the same probability. touch on. I've got, what's it say? Marion is doing something. What's Marion doing? Oh, yes, I remember. I recall. Now, this one's really different, like completely different from the one I just showed you, because this is a different type of question, because these are dependent things. These are dependent outcomes. One outcome affects the next outcome, right? So let's say, for example, I've got a bag with apples in it, two greens and one red apple. And you take one out, okay? And then you don't put it back in, okay? You don't put it back in. And so in the bag, left in, if you just take one out, there could be two greens left. There could be a green and a red, or there could be a green and a red, a green or a red, the other green. So I've got green one, green two, green one, green two, green one, green two. So those are the possible outcomes, yeah, of what you could happen after you've taken out one apple. So how does this work on a tree diagram? Okay, well, this time I'm actually going to go. I'm just going to go. There's only two ways of doing it. You can get red or green. The probability of a red was 1/3, and the probability of a green was 2/3. Now, what about the second time? After you've not put it back in, well, the numbers of, here we go, the reds and green. If you take out one red, the probability of getting a red the second time is going to be 0, yeah, because there are no reds left. And remember, the denominator is the number of possible outcomes. So now there's only 2 apples left, so that's going to be 2. And therefore, this one must be 2 out of 2. And similarly down here, though, it's all going to change because there's still one red apple, but there's only 2 apples left. And here, one of the green apples, there were 2, now there's only 1, and also that's going to be a half. Now, also just look at this. See, those 2 add together to give 1. Those 2 add together to give 1. So if you can get 1 and you're absolutely sure that it's correct, just do 1 minus the other one, and you've got your answer. Okay, so let's have a look at this question then about Marion, who is a sweetie eater. Marion has a bag containing 6 chocolates and 6 mints. She chooses a sweet at random and eats it, i.e., she does not put it back in. She then chooses another sweet at random. Right, copy and complete. But I'm not going to copy it. I'm just going to complete it because I know that's going to be a half. This one here, 5/11. Now, why has it gone to 5/11? Because she's taken out 1 chocolate, so that goes down by 1 to 5, and the total number of chocolates, total number of things was 12, and now that's decreased by 1 as well to 11. Mint, well, there's still 6 mints left, and there's 11 total sweets. And down here, if I choose a mint first, there's still 6 chocolates, so 6 out of 11, but there's only 5 mints. And that also correlates with what we were saying before, in that those two, the probabilities add up to 1. It's very important to also notice that it's not all of these probabilities add up to 1. It's only the ones in which are connected to one branch. So those 2 add up to 1. Those 2 add up to 1. Right. So work out the probability that 2 sweets consists of 2 chocolates. Okay, well, let's just do them all up here. Right, so we've got probability of chocolate and a probability of another chocolate. So that's going to be 6/12 times 5/11, which is 30/132, I think. Is that right? 11 times 12, yeah. Mint is going to be a 6 over 12 times 6 over 11, which is 36 over 132. Chocolate, mint, and then a chocolate is going to be a half times 6 over 11, which is 6 over 22. And this one down here is going to be a half times 5 over 11, which is 5 over 22. Okay, now this is that those ones here, they are going to cancel down just a little bit. I'm going to cancel it down to, I think, 22. Yeah, let's do that. So I still get 6 out of 22. And here, well, I don't have to actually work that one out because I know 5 plus 6 plus 6 is 6 plus 12 plus 5 is 17. So that must be 5 out of 22. Must be. Yeah, it must be 5 out of 22. So I've got all my probabilities there. Now, 2 chocolates. Well, we've worked that out. That's already worked out 5 out of 22. Question 2, a chocolate and a mint. Now, it could be probability of chocolate and then a mint, or probability of a mint then a chocolate. Okay, well, that's going to equal, we know that 6 over 22 plus 6 over 22 equals 12 over 22. If you leave it like that, that's absolutely fine. If you want to cancel it down, 6 over 11, that's also okay, same thing. 2 mints, we've got that, 5 over 22. And 4 is at least 1 chocolate, so probability of chocolate then mint plus probability mint then chocolate plus probability of chocolate. I'm getting hungry now. That's 6 over 22 plus 6 over 22 plus 5 over 22, which is 17 over 22. So you can see that with these ones here, they are a very, very different type of probability question. They are called conditional probability. That's what this is, because one directly affects the other. They are dependent on the outcome of the previous situation. Okay, so yeah, this is not super easy, but also it's not super difficult. You just got to be really careful and make sure that you've got a really good tree diagram. Now, the other one I've got is, I think I've got one more. That was page, oh no. Sorry, my bad. This is page 256. This is page 256. This one was also dependent. Really quick. Yep. Now it says a chocolate box contains, this is on page, what page is this? This is on page 259. Oh, sorry, the one about Marion, that was page, let's quickly check. Where's she gone? Oh, that was 252. Yeah, and this is 259. Here we go. Right. It says a box contains 2 maths books and 3 French books. A book is removed and replaced before another is taken. Hang on. No, this is wrong. Hang on. Oh, sorry. This is Sorry, I'm absolutely wrong. This is page 260. And it says a chocolate box contains 4 milk chocolates and 5 coconut sweets. Gina loves milk chocolates and hates coconut sweets. Oh. She takes 1 chocolate randomly and does not replace it before picking out another one at random. Calculate the probability that Gina is very happy. Calculate what is the probability that Gina is very unhappy. What is the probability that she gets at least 1 milk chocolate? Okay, so I'm going to start with my diagram, my tree diagram. How many different things can possibly happen? Well, there are milk chocolate, MC, milk, and the other one is coconut. Yep. So we've got milk, chocolate, and coconut. Now let's look at this. We've got 4 milk chocolates and 5 coconuts. So the probability of getting a milk chocolate is going to be 4 over the total number of sweets, which is or total number of things, which is 9. And coconut is going to be 5 over 9. Okay, she loves milk chocolates and hates coconut sweets. What an idiot. But anyway, what's the probability? And then she takes one out and doesn't put it back. So here we've got M and C. If she takes a milk chocolate, then that goes down to 3 and that goes down to 8. The number of coconuts doesn't change, so that's going to be 8, 5 and 8. Here we've got 4 and 8, and also this is going to be 4 and 8. The number of milk chocolates hasn't changed, but the total number of sweets has gone down by 1. And that's an M and a C. Now let's work out all of these. This is going to be 4 over 9 times 3 over 8, which is 12 over 72. This is going to be 4 over 9 times 5 over 8, which is 20 over 72. This one is 5 over 9 times 4 over 8, which is 20 out of 72. And the last one is 5 over 9 times 4 over 8, which is 20 out of 72. Now, just a quick checker, really, is that all of your final, all of these things here, they should add up to 1, because there's no other possible result. Okay, yeah. You can argue and say, oh, what if she vomits or something? No. Be simple. Keep it easy. Right, do they add up to 1? Yes, 20 plus 20 plus 20 is 60 plus 12 is 72. So we are good. Calculate the probability that Gina is very happy. So I'm assuming that means that she gets milk chocolate followed by milk chocolate, because if she got 1 coconut sweet, she'd be very unhappy, or she'd be unhappy. So I'm going to say that this one here is the answer to A. Probability that Gina is very unhappy. Well, 2 coconut sweets would make her very unhappy, so I'd say it's that one there. And what's the probability that she has at least 1 milk chocolate? Well, it's going to be those 2 together, add together to give 40 out of 72. Okay. Now, that right there is a brief overview of dependent and independent probability. So this one here is dependent. And that's this idea of a thing called given that. Okay. Now, this has got a very special way of being written as well, and I'll show you exactly what I mean by given that. If I do the probability of C given M, what does that mean? That means the probability of C happening after M has happened or has been chosen. Okay, so for example, this is just like a line. It's just probably C given M. Given that M has happened, what's the probability that C happens? So that this thing here would represent this line here, because it says that M happens, and then what's the probability that C happens after that? Now, yeah, so that's going to be our answer. Most probability of, C, given that M has already happened. So in this case here, the answer to probability of C given M would actually be 5/8, not 20 over 72. Right, I think that covers the bare bones, and I'm sure that you're all going to have a few questions, and I'm looking forward to doing some videos on this for any questions that you might have a little bit of difficulty on. If you do get the wrong answer, though, do have a look at your tree diagram. One of the issues about the answers in the back of the book is it's just a number. So it can be quite frustrating if the number you get is different from the number at the back, because it doesn't help you. Excuse me, it doesn't help you at all. But I think that should give you enough to be getting on with. I think this will take a good amount of time to get done. 1 week, 2 weeks at bare minimum. Yeah, so yeah, have fun. Guys, what's the probability of having fun? Probability of fun equals 100%. Maybe. Definitely.